So to understand any kind of design, we first should know that what is the basis of design, how a structure is designed. And I'm sure you must have covered a lot of this in your second year, third year, and even final years work, final years courses. And I will go through main design component and which are common for earthquake or gravity loads as well, and some are unique for winds only. The basic feature that we are looking for, basic design approach we are looking for, that it should have a complete load path. What do you mean by complete load path? The load from where it is generated, it should safely be transferred till the ground. And how it can be done? Suppose in case of wind, if your wind is hitting your window or maybe a slide gate, then those slide gates should be strong enough, those glasses should be strong enough to transfer wind load on the supporting frame. Those supporting frame should be strong enough to transfer that load to the closest beam or first slab, and then slab should be strong enough to transfer that force to the closest beam, and then beam to column and column to foundation, or maybe beam to shear wall and shear wall to foundation. This is called a complete load path. So it's very important. Even if you design something as basic as just gravity load without considering any kind of earthquake or without considering any kind of wind load, the basic thing is your load should be able to safely, your system should be able to safely transfer load from wherever it is occurring, from say 5th floor or 10th floor to the foundation level. And now something which is very specific to wind design. So in wind load, we are dealing with wind pressures. So whenever wind hit on your window or your wall, it is having some particular pressure, and there is also wind or air inside your structure. So there is external wind which is having external pressure, and there is internal wind which is having internal pressure. So because of this equilibrium between internal pressure and external pressure, your building doesn't blown up or crumbles down. So here one important thing is internal pressure is plus and internal pressure is minus. You can see on the left and right. So when is the internal pressure plus? When it's try to expand the structure. And when is the internal pressure is minus? When it tries to pull the structure towards the common center or center of the building, center of the room, you can say. But the external pressures are just opposite. That on the left hand side, all the negative pressures are pressure which are trying to expand the volume of a building. But positive wind pressure is something which is trying to compress the structure. So just keep these two things in mind, that signages are negative. So you can see here that plus thing, what plus is internal pressure and what minus for external pressure, but they both are acting in the same way. Direction is the same, but scale is minus. So where whatever is plus for internal is minus for external. Similarly, whatever is minus for external is plus for internal, and vice versa. Here you can see that the wind is entering through a door or window, and then it will try to expand the entire building. So that is plus internal pressure. But here, if you see that the side on which wind is acting is closed, but the opposite side is open. So because of this wind force, which is going, the wind blow, which is going across the building and then trying to suck out the wind which is inside the building. So that's how the internal pressure is created. So that's why I say that wind is not same as earthquake, because when we are having in plus direction, minus direction, that's the thing. Two things are totally different. So here is one more example here, how plus and minus are different. So here you see, suppose this is the x direction and perpendicular is the y direction, and plus wind tries to go towards the building, but the this is called windward side, the face which is facing the wind, and the back side is known as the leeward side, and these are two across sides. So across sides are always pushing, the face are pulled apart. Similarly, the back side or leeward side also, the building is try to be dragged in the wind force direction, and wind force acting in the x direction, so it is pushing wind in plus x direction. Similarly, if the wind is in minus x direction, so these are the forces, and perpendicular to the wind face, it is always opposite direction because of across wind effect, and vertical thing is something which is always tried to lift up. So unless it is a slope and which is having a significant angle from the horizontal, this is always uplifting force. And then again, coming to the plus y direction and minus y direction. So these are the peculiarities of the building. And if you can, as you can see, that this building is not symmetric from any side. So plus x is different from minus x, plus y is different from minus y. So you have to take different forces, different combination for all the four things. And when the codes are stringent and you are designing a very tall building, you may have to see the attack of wind from 15-degree interval or 30-degree interval, or maybe 45-degree interval at least. And then coming back to the design basis, which is common with the all other force types like dead load, gravity load, or earthquake load, is limit state. We have two types of limit state defined in the IS code, is limit state of serviceability and limit state of strength. So serviceability strength is something which has to do with the in service thing. So when you are using building on day-to-day experience, it should have deflections within the limit, and it should have cracking within the limit. And then there is a strength. So in case of extreme wind event or in case of extreme earthquake force, the building should not collapse and kill the people or trap the people. So there are two limit states are designed, two limit states, and both should be satisfied by the building. Now coming to the, as I said, I will not go to the details of IS code, but there are some important changes which this IS code has brought. So we will quickly go through those changes, and then we will finish the our presentation discussion today evening. And one thing is VZ is that is wind load at the height, which is VB, and to K1, K2, K3, K4. So K2 factor has changed. So earlier it was terrain, height, and structure size factor. So it is no more, height is not kept, but terrain is not kept. So it is roughness and height factor. So structure size earlier, based on if the largest size of structure is less than 20 meter, then it was category A. And if the largest size of the structure between 20 and 50, then category B, then, and largest size more than 50, then it was category C earlier. But that condition has been removed. So it's only now terrain, which is mean the roughness thing, and height, how high the building is. And building, as I said, building classes have been removed, and all the values of course, for the category A. So if you compare the K2 values from the previous code and this code, you will see that K2 is from K2 for class A of the last code. Then we see that in last code, there was no K4 factor. There were only VB, K1, K2, K3. K4 factor is something new, which is added to our code, and this gives the importance for cyclonic region. So whenever a structure is lying in the area where there's a cyclone prone area, then additional factor of 1.3 is important. And for industrial structure, it is 1.15. For all other structures, it is 1. This is how you incorporate the design for cyclonic. Then there is one modification regarding the gust wind factor. So let's talk about early mean wind speed formula, and turbulence intensity formula, and then interference design. So as if you remember, we had talked about doing the analysis of multiple buildings through wind tunnel. So how different buildings will affect overall thing on my building. So this is the something which is interference guideline is there. So if suppose this is structure is there, then different interference zones are defined in the code. That zone Z1, Z2, and Z3. So zone Z1 where is the maximum effect will be there, then zone Z2, Z3, and Z4. So the effect will be less and less. And coming to the gust factor method, this method was there earlier as well, but in this code they have improved it a lot. They have put many formulas, background formulas, which were not there earlier. It was shown only in terms of either graph, but graph, they are not very effective, because you are half a millimeter here and there in the graph, and your value might change drastically, and the design by person X and person Y can be very different in that case. So to get rid of that, they just have introduced formula. So formula based on which the graph is eventually developed. So similarly, size reduction factor formula, effective turbulence formula, and energy ratios. These formulae you can find out. And earlier, for the Gauss vector method, there was no across wind response calculation formula. Wind not only make structures move in the direction it is blowing, but it also tries to push it in perpendicular direction. So for the Gauss vector method, this methodology was not there. So this methodology has been put for across wind response. Coming back to the conclusion, or what we have learned, seen from the last 40-45 minutes talk, is wind is very complex. It's not very intuitive. You can think about one thing and that will result into another thing. That's not so straightforward in case of wind. So that's why we have several empirical factors that are dependent on experiments, which you cannot calculate using straightforward your methodology or mathematical formula. And that's why it needs thorough understanding. So as somebody, if somebody has designed a chimney and has not put those helical strips to break the wind flow, then whatever design you may have done, however diligently you have done, but if that understanding of a particular effect is not there, then you might be constructing an unsafe thing. And coming back to the things we have discussed, that we have new evaluations method nowadays, like CFD, computational fluid dynamics. So this is something which was very much used in for aircraft design or wind flow design across the aeroplane, but the tools are now capable of doing it for a more complex thing, like a cityscape. We have seen one contour plot for that, where CFD analysis was done for multiple buildings, and how wind pressure will be higher or lower depending on the area, depending on the place you are within the city. Most important thing that I would like to say, that knowledge is very essential. So when you are at the beginning of start of your career, give most time and most stress on knowledge development, understanding the key concepts. Computational tools keep on evolving and giving you more and more power to do the calculations, but we have seen that if you don't understand the basic concepts, then softwares are of no use. So that's my biggest, you can say, underlying lesson or underlying statement in this. Spend maximum time on your knowledge, how you build up your basic concepts. The need for capable engineer is much more than any time we had in the past, because we are having a growing up cities. We are going taller and taller. For a city like for Mumbai or Gurgaon or Delhi, the demand of high scraper has been increasing. If you see a trend of over last 10 years, temporarily it is a little bit down because of COVID situation and a related uncertainty in economy. But definitely we have to build a huge infrastructure for our country. Infrastructure includes bridges, industrial facilities, transmission towers, cooling towers, you name it, and there will be factories, so you will need chimneys. Understanding all these things, and add with on top of that, that civil engineering thing is going through a lot of additional changes. A lot of new codes are being introduced. If you have heard that there was a new code which was introduced in 2015, that is IS 16700, that was only for tall buildings. So that was not there earlier, but it is there now. So if you know knowledge or tools like this, if you are aware of the things, then of course you have a bright future in the civil engineer. So I started from IIT. I did my BTech and MTech in 2003, and then I worked with the industry, worked on some challenging project with my professor, and then later on joined IIT Bombay itself for the PhD. And I find this thing very challenging. Not many of my colleagues or my friends from IIT days are working in such a challenging thing. And of course, when you go to the field, then there are a lack of capable engineers. Have your right kind of skills and right kind of mindset, then nobody can stop you. And with that statement, I stop here.